Hello everyone, let's go over the fundamental theorem of calculus and antiderivatives at the same time. Alright, so this is going to be different than our usual videos posted because this is going to be more like our regular class here, okay? So this is just for you guys. Alright, anyway, so I figure since we are towards the end of the semester, we should probably talk about the fundamental theorem of calculus. Okay, it is the fundamental part, probably the most important thing from calculus altogether. But before we do that, we need to talk about antiderivatives, which is basically the opposite of a derivative. Derivatives. I think I spelled that right. Antiderivatives. Okay, so remember if you had a function or an expression like x to the fifth, okay, and you wanted to find its derivative. Okay, this is one of the notation that we could use, a little apostrophe or something like that. Okay, if we want to find its derivative, remember we would take the exponent, bring it down to the front, and then subtract 1 from the exponent. Okay, that's what we're about to do here. 5x to the fourth, right? That would be our derivative. Okay, well, what if I wanted to undo that? Okay, if I wanted to undo the derivative, that's the antiderivative, okay, which means to do the opposite. Okay, and usually the way we'll write this out is with this, what we call an integral. An integral, okay? But basically when you see that, what you need to know is that means that you're about to find the antiderivative, okay? And then also at the end here, you'll put this dx, that is the differential. You don't have to worry too much about what that means. All you need to know is that I am going to be finding the antiderivative of this piece inside. You're always going to see this integral with this dx paired up together, okay? So kind of treat that as its own thing. They go together. Okay, so how do I find the antiderivative? Okay, well, for something like this, we just do the opposite of what we just did to find the derivative. Okay, so what does that mean? All right, so what did I do? First thing I did, let me write down the steps. Maybe that'll help us see it. Let's use pink. To find the derivative, the first thing I did was I brought the exponent down, or I multiplied by that exponent, right? Okay, that was the first thing that I did. I multiplied x to the fifth by the 5, right? So I brought it down, but really I multiplied it by 5. Okay, the second thing I did was subtract 1 from the exponent. Okay, that was the steps for the derivative. Well, the steps for the antiderivative, let's go with purple. Antiderivative. Okay, it's going to be the exact opposite. I'm going to reverse this. So instead of starting with multiplying by an exponent and then subtracting 1 from the exponent, I'm going to start at the bottom here where I would subtract 1 from the exponent, but I'm going to do the opposite. I'm going to add 1 to the exponent. And then I'm going to do the next thing, which was originally the first thing. Okay, so the next step would be to, instead of multiply by the exponent, I'm going to divide by the exponent. Okay, so add 1 to the exponent, then divide by the exponent. That should give me my original problem, right? So let's see. Let me get all this out the way. All right. Okay, so this equals, let's try it out, 5x to the fourth. First thing I'm going to do is add 1 to the exponent. That's going to give me a 5. And then I'm going to divide both sides by that new exponent. Okay, so 4 plus 1 is 5, so I'm dividing by 5. Let's simplify that. So that's 5x to the fifth over 5. Of course, those 5s will cancel, and that leaves me with x to the fifth. Oh, look at that. I undid the derivative. Okay, that's the antiderivative. Okay, so now, what does that have to do with the fundamental theorem of calculus? Okay, well, we'll get to that. in a second. Although I do need a comment real quick before I not answer this question all the way. Okay, so when finding the integral, slightly different than finding the derivative, okay? When finding the derivative of x to the fifth, I got 5x to the 4th, right? If I found the derivative of x to the 5th, I get 5x to the 4th. Well, what if I found the derivative of x to the 5th plus, I don't know, 8? If I found the derivative of that. Well, this would be 5x to the 4th. And this right here would be 0, so it's gone, right? It wouldn't be there anymore. So it's possible that when I find the antiderivative, there could have been a number that was right here, right? Because if I found this one's derivative, it would bring me back to that. Okay, so since there could have been a constant number, you need to account for it. So I'm going to put a C right there. Okay, that's the antiderivative. The antiderivative is going to be what we just did with the exponent and all that, plus a constant. Okay, at least that's going to be the integral. Okay, so anytime you have to find an integral. Okay, so now that I've said that, let's actually do examples. Okay, so that was just me making up stuff on the fly. All right, so let's find the integral. This is called the indefinite integral. You'll see why later. This is the integral of 9x to the 4th dx. Okay, and remember I did say that this integral and this dx always go together, so you can really ignore them in general. I'm focused on this inside piece here. Okay, so 9x to the 4th. Well, the rule, if you remember, is add 1 to the exponent. So 4 plus 1 is 5. Then divide by that exponent. 9x to the 5th over 5 plus a constant c. Okay, so hopefully it's not that bad. It's just as easy as finding the derivative, just, you're doing the opposite. Okay. Okay, let's find the integral of x to the 4th over 7. Okay. X to the 4th, add 1 to the exponent. That's going to be the 5th. Divided by 5. Okay, well, that if I'm doing divided by 5, that just means stick the 5 down there in the bottom. So that's 7 times 5. There you go. But don't forget, plus the constant c. Okay? So again, when you're dividing something that's already being divided, so in other words, this is already being divided by 7. Now I'm also dividing it by 5. That's the same thing as dividing it by 35. Okay, so just want to remind you of that. Let's do one more of these. Okay, this one's a little different. If you see that you have something like 4 over x to the 3rd, remember when finding the derivative, you wanted to rewrite it to where you just had a negative exponent. It just made it easier to work with. Well, the same thing is true for antiderivatives. So I'm going to rewrite this as x to the negative 3rd power. It's the same thing. Okay, so now to find the integral, I'm going to add 1 to the exponent. So negative 3 plus 1 is negative 2. Then I'm going to divide by that negative 2 plus my constant c. Let's clean that up a little bit. 4 divided by negative 2 is negative 2. X to the negative 2nd power plus c. And I don't know, I just want a positive exponent this time, so I'm going to write it like this. Okay, they're both the same thing though, the two expressions. Okay, so negative 2 over x squared plus c. Again, c is the constant. Now, remember, you can always test this out as you're working it out, right? Let's test this out. Let's say I want to make sure this answer is correct. Well, then just go and find the derivative of what you just found. You should get the original expression back. Okay, well, let's rewrite this as a negative 2x to the negative 2nd plus c. The derivative, negative 2 times that negative 2 in the front, would give me a positive 4 x to the Subtract 1 from the exponent. Negative 2 minus 1 is negative 3. The derivative of the constant here, of course, is going to be 0. And if I clean this up, I get 4 over x to the third plus 0. And that is the original, right? So check. I know this one's right. Okay, so that would be the indefinite integral. Next up is the definite integral, okay? And this is where the fundamental theorem of calculus comes into play. So maybe I'll go up real quick and write out what you need to know about the fundamental theorem. Okay, so if you need to find the integral of a function on an interval a to b, in other words, you have a, b, and you have some kind of a graph that does something. Okay, what you're trying to calculate with this is the area from here to here. You're trying to calculate this area. Now, if this is a nice, pretty shape, let's say you have a graph that looks like this, and it's just a flat line, right? You just have a straight line. Oops, that's ugly. Finding that area wouldn't be too hard, right? All you would have to do is just find the length here, find that there, multiply those together because it's a rectangle, right? But in this case, and most other shapes, they're not going to be nice, pretty rectangles or triangles. They're going to be some kind of odd shape, okay? So to find that area, you can use the fundamental theorem of calculus, which just says find the antiderivative of the function f. That's going to be capital F to represent it. Okay, let me write that here. Let f of x, capital F of x, be the antiderivative of little f of x. Okay, so f of x is the function. Capital F of x is the antiderivative. Okay, so if I want to find the integral, which again is this area here, okay, I will just find the antiderivative, plug in the top number here, minus the antiderivative with the bottom number plugged in. Okay, that's the fundamental theorem of calculus. You can calculate any kind of weird area defined by a function and an axis by just finding the antiderivative, plugging in some numbers, and subtracting. It makes finding areas a whole lot easier. Now, if we were still meeting like normal, I would go into detail about how you go and find the area without this and how tedious of a process it was. It was quite terrible, okay? But we don't have to worry about that. Yay. All right, so anyway, let's find the definite integral. In other words, let's find the area under the graph of 9x to the fourth between that graph and the x-axis, okay? From negative 1 to 3. All right, what does that look like? Let me just do a terrible sketch of the graph here. All right, so x to the fourth, 9x to the fourth probably looks something like this. Looks kind of like a parabola, but worse. Okay, negative 1's here, 3's over here somewhere, so I want this area, right? That's basically what we're trying to find here. Okay, since it's not a nice triangle, right? It looks kind of like a triangle, but it's definitely curved, so it's not. I need to use the fundamental theorem. Okay, so what I'm going to do is find the antiderivative of 9x to the fourth. We did this earlier, but I'll do it again. 9x, add 1 to the exponent. 4 plus 1 is 5. Divide by that exponent. It's 5. Now, you don't have to worry about the constant c. Okay, when you're doing the definite integral, whenever you're given numbers here and here, you don't have to worry about the plus c. All right, this is a different notation that we probably haven't used before, but I'm putting a line right here and putting a negative 1 and a 3. In other words, that's my reminders that I have to plug in those numbers and subtract the difference. Okay, so I found the antiderivative. I'm going to evaluate it from negative 1 to 3. That means 9 times 3 to the fifth over 5. That's me plugging in 3. Minus, same thing, except this time plug in the negative 1. 9 times negative 1 to the fifth over 5. Okay, that's what we mean by capital F of A. I'm sorry, capital F of B minus capital F of A. All right, what in the world is 3 to the 5th power? Break out my calculator because I don't really know. That's 243. That's it? Oh, I should have known that. Times 9 divided by 5. And fancy calculator here. It says 2187 over 5 minus, oh, this one's easy. That's going to be minus negative 1 to the 5th power is negative 1 times 9 is negative 9 over 5. So that leaves me with plus 9 over 5. So that leaves me with 2196 over 5. Or, if I wanted to write it out as a decimal, I could. That's fine. 439.2. So that'd be the area. And that does make sense. It's going to be a large area because this 9x to the 4th, that means this thing goes way, this thing goes way up here, okay? So, it could be 100 or something, I don't know. So all of this area is calculated and you get 439.2 square units, whatever the units happen to be. All right, let's do another one. Okay, we did find the integral of this one already, the antiderivative, but we'll do it again. Okay, so x to the 4th, add 1 to the exponents, x to the 5th, divided by 5. That's going to give me 35 on the bottom there. Evaluate it from negative 2 to positive 2. Okay, well, let's plug it in. So it's going to be 2 to the 5th over 35 minus negative 2 to the 5th over 35. That's 32 over 35 minus negative 32 over 35. Of course, the two minuses make it a plus, so that's 64 over 35. 64 over 35, and if I divided that out, that would be, the fraction here is better because you have to round the decimal here, 1.8 to 9. Okay. Finding some areas here. All right, and let's do this weird one. And this is our last example. Okay, so remember we did rewrite this one as 4x to the negative 3rd power. So its antiderivative, add 1 to the exponent, negative 3 plus 1 is negative 2, divided by negative 2. And we're going to evaluate this from 2 to 8. When we cleaned it up earlier, we ended up with negative 2 over x squared. Evaluate it from 2 to 8. Okay, let's plug it in. So negative 2 over 8 squared minus negative 2 over 2 squared. Negative 2 over 64 plus 2 over 4. Oh man, what's that going to be? Okay, so that's going to be negative 1 over 32 plus 1/2, but I don't want 1/2. I'm going to make a common denominator. I'm going to multiply by 8 over 8 because 2 times 8 is 16, but 4 times 8 is 32. And so negative 1 over 32 plus 16 over 32 is 15 over 32 square units, or whatever it is we happen to be working with. And 15 divided by 32, if I want a decimal, is 0.4685. Okay, now we're out of examples. So that's the fundamental theorem of calculus. Look at that, you've learned calculus. Way to go.